All right, hello everyone, and welcome to my channel. This channel is for educational purposes. We usually look at different theories of everything and go deep into them and just try to let you know what they're all about and how you can benefit from them. Today is our 461st, I believe, 61st video on the reciprocal system of theory from Mr. Dewey B. Larson. And in 1959, Mr. Larson proposed his two fundamental postulates about how he believed the universe operated. He elaborated those postulates through a process of deduction to arrive at a theoretical universe, what his universe would look like if his fundamental postulates were correct. And then he wrote some books. Many of them looked at his predictions, his theoretical universe, and compared them with the measured universe of the scientists that they had compiled in their scientific tables through their laboratory experiments and their observatory viewings, I guess. And we're looking at one of those books today, Basic Properties of Matter. This book is on chemistry primarily, and Larson comes up with equations for many of the basic properties of matter, then applies his equations to many of the forms of matter, the elements in the periodic table, and many compounds, especially organic compounds. And then he compares his results with the scientific tables. We're looking at chapter 7 in this book called Temperature Relations, where he goes into the kind of the formation of the temperature scale. In the previous chapter, specific heat patterns he goes over. I guess one of the fundamental findings that Larson makes is that the temperature is really taken on a molecule by molecule basis. Every molecule has its own temperature, and they all have different patterns of how efficiently they heat up or their specific heat, and they are kind of figured out through quantum measurement. But then now he's attempting to take the quantized measurements of all the different atoms and compounds, and then to find the common denominator with the temperature scale. And it's a little bit in the weeds, but we want to go over it just to kind of see how Larson thinks about the reciprocal system. But obviously, first we want to know a little bit more about the reciprocal system. The basic idea, Larson's reciprocal system is also called the universe of motion. And Larson is not the first, but the first really successful attempt to formulate a universe based on motion. The ancient Greeks would base their universe on matter, and then Einstein and Heisenberg and some of the others came along and maybe said, well, it looks like matter, but it's really energy. They tried to establish a universe based on energy. Other people have looked for the unified field theory, how to unify the four fundamental forces. But Larson starts his quest here on motion. And his first postulate, which is really the main postulate, and for all intents and purposes, the only postulate, because the second postulate is really just kind of related to math and geometry, and it's really for taking that first postulate and then the rules of deducing from there. So the first postulate is what we'll focus on, and the first postulate reads that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so the universe is made out of motion. Motion is the relationship between space and time that entails a reciprocal relationship between space and time. Space, time, and motion come in 3 dimensions, and space, time, and motion come in only discrete units. And then he goes from there, but just a few finer points. When Larson's referring to motion, he's really referring to a scalar motion. This is a more generalized kind of motion, a motion that has a magnitude, but it has no direction. The general visual that you would use for that is a balloon that you put dots on. As you inflate the balloon, all of the dots will be moving away from each other. So they're moving away from each other, but they're not moving in any specific direction. Every dot is moving in every dot is moving away from every other dot. And really every location on the surface of that balloon is moving away from every other location. So every location is moving away from every other location, meaning every location is moving in every direction. So there's no specific direction. That's a scalar motion, and that's really just like one dimension of 3 dimensions of motion. And if you inhale and then you deflate the balloon, all of the dots will be moving toward each other. Larson refers to these as the outward motion as the progression, and the inward motion as gravitation. Now, we've got the universe is made out of motion. Motion is the relationship between space and time. The relationship between space and time is expressed in a fraction. All motion is a fraction with space or time as the numerator and time or space as the denominator. So one is the numerator and the other is the denominator, and they all can come in 1, 2, or 3 dimensions. You can even get up to 6 dimensions when you are multiplying them by multiplying. You probably could get even more than 6 dimensions if you're using like a compound entity. Now, if we look at something like the most basic kind of motion, speed, the bike is moving 10 miles per hour, 10 miles of space in 1 hour of time, space over time. So speed is space over time. And that is a reciprocal relationship, which you can see if you double the speed and say the bike is moving 20 miles per hour. Now you can also say equivalently that the bike is now moving 10 miles per half hour. You can multiply the space or divide the time. Either one is the same, and that is a reciprocal relationship. Larson extrapolates that to all forms of events or scientific phenomena are forms of motion. So that includes matter. Matter is a kind of motion. Energy is a kind of motion. Pressure is a kind of motion. Force is a kind of motion. Acceleration is a kind of motion. Power is a kind of motion. Viscosity is a kind of motion. Electric charge is a kind of motion. All of our scientific entities, and so everything has their time-space signature, or space-time signature. And this is a great system. because it improves upon the MKS system, because the MKS system uses meters, kilograms, and seconds. So it's using time and space, but it's also using mass. That's 3 variables instead of 2. By defining mass, as Larson does, as time to the 3rd power over space to the 3rd power, he eliminates the mass term, and now we just have 2 terms instead of 3, and that simplifies things massively. Okay, now we also have the 3-dimensionality of space, time, and motion. Now you can clearly see the 3-dimensionality of space. This is our normal environment, X, Y, Z coordinates in a still frame, a still background. This is, the container viewpoint of the universe, that we are moving through space and events are unfolding in time. Larson calls this the spatial reference system, coordinate time, and clock space. So coordinate space and clock time. Time is always getting later and later and later, but in no specific direction. Time is moving in a scalar manner, but space has been stilled, and we see it in 3 dimensions. Now, by the reciprocal postulate, there would be some other area in space-time, in the universe, where we have the opposite, or the reciprocal of that, meaning that we have 3 dimensions of time, coordinate time, in a still frame, and space is the property that is still scalar or still progressing, like on the surface of an expanding balloon. Larson calls that the temporal reference system, coordinate, time, and clock space. Space is always getting farther and farther and farther apart. Now, that's really like your 3 dimensions of space and your 3 dimensions of time. Now, but in order to express 3 dimensions of space or time, you only need 1 dimension of motion. Think of something moving through 3-dimensional space. That's just a 1-dimensional motion. And there are 3 dimensions of motion. So, it goes beyond that. Now, also you have so there is no reference system. The spatial reference system and the temporal reference system are not capable of expressing multidimensional motion. But Larson has what he calls the natural reference system, and this is defined by the discrete unit postulate. Universe, space, and time and motion come in only discrete units. You have to have a full unit before you have anything. Everything is quantized. 1 unit of space is approximately 2 millionths of an inch. 1 unit of time is approximately 1/6 quadrillionth of a second. And if you have 1 unit of space in 1 unit of time, space over time being speed, then you have what Larson calls unit speed. Turns out all of our scientific entities, all the time over space entities, units that we talked about earlier, they all come in units. They all are quantized. But in this case, we're talking about speed. 1 unit of space in 1 unit of time is 1 unit of speed. And Larson calls that unit speed. It's also known as the speed of light. And this is the speed of the progression. The progression is always progressing at 1 unit of space per 1 unit of time. 1 unit of space per 1 unit of time. And this occurs omnipresently, everywhere, and at all times, eternally. So that is what Larson calls the null point, or like the 0 point, the neutral point, the state of rest of the universe of motion is motion outward in all directions, at all times and all places, at the speed of light. So This is your empty universe. When you don't have anything else in the universe, you have motion outward at the speed of light in uh, all spaces and all times. And Larson refers to that as the progression of the natural reference system. So this is the reference system that the universe actually conforms to. The spatial and temporal reference systems are special stationary reference systems that we can use for measuring. Science has used the spatial reference system as its normal reference system. Larson uses it as a kind of an abstraction. It will deliver measurements, but it's not giving you a true picture of what's actually going on, like the moving reference system that he calls the natural reference system, the progression of the natural reference system. And this also means that half the universe is moving faster than the speed of light, and half the universe is moving slower than the speed of light. The half that's moving faster is pretty much unknown to science and blasphemy to science, but Larson refers to this as the cosmic sector. And the half that's moving slower than the speed of light, which we know all about, which is the sector we reside in, Larson refers to this as the material sector. And all of the things that we know about the material sector can be extrapolated to the cosmic sector by the reciprocal postulate. All we have to do is reverse the roles of space and time. When we cross that unit speed boundary, we invert the roles of space and time. So, for example, in the material sector, you have coordinate space and you have clock time. In the cosmic sector, you have coordinate time and clock space. Now, within each one of these sectors, there is a subsector or a subregion that has to do with the discrete unit of both space in the material sector and time in the cosmic sector. When atoms and particles move closer together, they get closer together until they are apart by 1 unit of space. And once they get 1 unit of space apart, they cannot approach each other any closer, because 1 unit of space is the minimum that can exist by the discrete unit postulate. You have to have a full unit of space before you have space. So within 1 unit of space, they cannot move in space. So what they do instead is they move further apart in time. They move outward in time. And by the reciprocal postulate, outward in time is the equivalent of inward in space. And so we see it as they are still moving inward in space, because we only see space because we are in a gravitationally bound spatial reference system. And so we see space, we don't see time. But what Larson calls it equivalent space. The activity is actually occurring in time, but we see it in equivalent space. But when we see it in equivalent space, there are a few caveats. We have to reduce the results of our observations, and also recognize that what we're seeing is a second power of what we normally see. So those two things have to be taken into account. Whenever you cross a boundary into a different region or sector of the universe, you have to apply this. One of these is called the interregional ratio, which is basically what you lose in the translation when you cross a boundary. And when you cross a boundary, Larson refers to this as the time region, because there is no space. It's within 1 unit of space. And so everything within 1 unit of space is in time only. And space remains constant at 1. And whenever you cross that boundary, the rules invert again. And now the progression is the inward quantity in equivalent space, and gravitation is the outward quantity in equivalent space. The same is true in the cosmic sector, except in reverse. In the cosmic sector, you have the space region within 1 unit of time. And that is the result of cosmic atoms and cosmic molecules approaching each other to 1 unit of time. And they can't move any closer, so they move in space instead. But a viewer in the cosmic sector would see it still in time because they're anchored to a temporal reference system. Okay, now finally, atoms come from basically matter. It comes from the source, which is the progression of the natural reference system. It comes from taking that outward motion and reversing it in a number of different ways. First, you have to reverse it through a vibratory motion, which is a photon. And you're really reversing the progression in one of space or time, but not both. Remember, the progression is 1 unit of space per 1 unit of time. But if you reverse one of those two things, then you really have the photon. And then the photon, it gets rotated. You have to rotate it once just to nullify the progression in the other. And then that is what he calls the rotational base, which is the rotational equivalent of nothing at all. And then that rotational base needs to be rotated in 3 dimensions in order to form an atom. And so Larson's atom has 3 numbers. Each one of the atoms in the periodic table has 3 numbers. A 2-dimensional rotation, primary 2-dimensional rotation, a secondary 2-dimensional rotation, and those two alternate 1, 0, 1, 1, 2, 1, 2, 2, 3, 2, etc. And then you also have an oppositely directed 1-dimensional rotation that is optional. It can be 0. It's 0 in the inert noble gases. And then in electropositives, it is positive, and in electronegatives, it is negative. So those 3 numbers are what Larson uses to determine his the numbers that he puts into his equations for these various basic properties of matter that we're about to go over. So let's just read from here, and you'll just try to pick up some breadcrumbs. You're not going to really understand this in total. I'll try to clear up some things, but if I tried to clear up everything, it would be, pretty much twice a sentence I'd have to be interrupting. So, but the main point, the main idea is that you just want to understand that this is a generalized theory. So if you can learn how it operates in chemistry, you also learn how it operates in astronomy, and you learn how it operates in economics. And so it's worth investing your time and energy into learning the reciprocal system because it applies to every subject. Unlike if you want to study astrophysics or you want to study organic chemistry, everything you learn, within those legacy science fields is pigeonholed. You learn one subject, and that's all you learn is that one subject, and it has no application outside of your field. But this has infinite application. Okay, but this equivalence of the 1-1-1 compressibility and 1-1-0 temporal factors. Now, when you have when you're in the time region, you're really an atom in the solid state. Basically a group of atoms that are all geometrically, so-called bonded together. They are beset with 2 basic forces. The force of the progression is really seen as an internal pressure, and the force of gravitation is really seen as thermal motion or heat. And so those pressure and temperature are the main, forces that atoms are dealing with when they're in the solid state, in the time region. So he formulates equations for the compressibility and for heat, and they're different. The compressibility numbers, you multiply them together. The three numbers you multiply together. With heat, the three numbers you add them together. Okay, so this equivalence of the 111 compressibility and the 110 thermal factors does not mean that the 111 and the 110 are equivalent. The 111 thermal factors is the minimum for a substance with effective rotational displacement in all three dimensions, where the thermal factors drop to 110, as indicated for rubidium and cesium. There is no effective displacement in the electric dimension, and the thermal, that's the third number, the electric dimension. The first two numbers he calls magnetic dimensions. The magnetic dimension is two-dimensional, and the electric dimension is one-dimensional. And the thermal motion is following the inert gas pattern because it has a zero as the electric rotation, the third one. Such behavior is uncommon, but it is not without precedent. In other properties, we found in Chapter 1, for instance, that a number of elements, including the halogens, the elements corresponding to the alkalis on the opposite side of the inert gases, have interatomic distances in one or two dimensions that are similarly based on magnetic rotation only. So he's saying that in certain circumstances, the alkali metals and the halogen gases are behave as if they're inert gases, the element right next to them on the periodic table that has a zero for its third number. Since the empirical values listed in Table 22 are subject to a considerable degree of uncertainty, small differences between them and the calculated values have no significance. In some cases, however, the discrepancy is large enough to be real, and further study of the thermal relations of these elements will be required. Only one of the experimental values shown in the table, one of those applicable to chromium, is too far from any theoretical temperature to be incapable of explanation on the basis of the theoretical information now available. As brought out in the discussion of the general pattern of the specific heat curves in Chapter 5, in many substances there is a change in the temperature scale of the curve at the first transition point, T1, as a result of which the first and second segments of the curve do not intersect at the 2 1/3 R endpoint, which is the end of the first transition. So the transition is really an inflection point in the specific heat curve where the curve takes a new rotation. It goes into the second rotation. The atoms are based on rotations, and it moves to the second of the rotations, and this serves to basically increase the temperature scale and really so that more heat can be added without having the atom move closer, much closer to the melting point. Because by probability, the atom wants to stay in the solid state at all costs. And so it does everything that it possibly can when it's heated up. It does everything that it possibly can to avoid getting close to the melting point. And so one of the things it does is it starts making these transitions, if possible. And he went through this in Chapter 5 and 6 on specific heat. As a result of which the first and second segments of the curve do not intersect at the 2 1/3 R endpoint. The R, it's really total of the specific heat, quantized specific heat. Endpoint of the lower segment of the curve in the normal manner. This change in scale is due to a transition to the second set of thermal factors given for the elements in which it occurs in Table 22. With the benefit of the information that we have developed regarding the factors that determine the temperature scale, we can now examine the quantitative aspects of these changes. As an example, let us look at the specific heat curve of molybdenum, which, as previously noted, also applies to ruthenium. The thermal factors available to these elements at low temperatures are 4, 8, 2, identical with the compressibility factors. But again, you multiply the compressibility factors while you only add the thermal factors. The first transition point, the specific heat 4.63, that's 2 1/3 R, is reached at 128 degrees Kelvin on the basis of these factors. The corresponding, that's because the specific heat, the thermal factors are 482, which adds up to 14. And then you need to multiply that 14 by 9, or by, it's really 8.98, which is the conversion rate that you use for the second segment of the curve. He determined that it's basically 1.995 times 9/2. The first number is 1.995, and then the second transition is 8.98. So you multiply the thermal factors, 4, 8, and 2, you add those together to get 14, and then you multiply that by 9, or 8.98, so that's where he gets the 126 number. 126 degrees Kelvin on the basis of these factors. The corresponding empirical temperatures determined by inspection of the trend of the experimental values of the specific heats are 129 for molybdenum and 128 for ruthenium, well within the range of uncertainty of the techniques employed at estimating the empirical values. Okay, so we're going to stop there, and we'll go on with investigating more about these specific heat curves and the temperature scales next time. Thanks for tuning in today, and keep it up. You know, you're doing a great job. Just hang with it. You'll learn more than you'll ever expect. Thank you.